Hello everyone, this is Angelo from Neurocraft. In today's video we are going to talk a little bit how we are going to model our data to work inside the deep neural network and a core concept called vectorized format. So let's start by saying that deep learning works with a large amount of data in many different types and formats that even the learnable parameters itself have to be modeled in some way. And when we have this data containing multiple elements organized inside a structure, we simply call that structure a container. And vectorized format is when we store all the elements inside this container sequentially inside the memory, despite its representation, okay? Now, before getting into code, why do we need this format in the first place? So the first reason is because it's more memory efficiency, since we don't need to retrieve the full data searching in different parts of memory. The second reason is because it's easier to process element-wise, and that happens a lot inside our deep learning, especially with the activation functions. And the third reason is to unify all different data types inside a single algorithm to process them all. Otherwise, we should have to construct a single method to process an array, another method to process a matrix, another one to process an image, and so on. And to make things more clear to understand, let's see the main difference between data representation versus data storage. So while on the left we can see three examples of data structures and its representation like an array, a matrix for a QR code for example, and a three-dimensional tensor for an image, on the right side we can see its representation in a vectorized format, meaning in a sequence of elements, without clearly distinction between how many elements by dimension we have. So starting by the first example on the left, the array, with just a single dimension width, we can see that its elements are already stored in a vectorized format. So there is no difference between its representation and its storage. Now for the second example, that is a QR code represented by a matrix, its elements are represented by rows and columns, but when we convert it to a vectorized format on the right, we lose this information in exchange for a more memory efficient way at the same time as an easier format to work, since we can apply the same algorithm to process element-wise both data structures, either the matrix as well as the array. And last but not least, we have a three-dimensional tensor represented by an image, composed by channels, height and width, which if we see on the right, its vectorized format follows the same rules as the matrix and the array, multiplying its dimensions together to obtain the total size of required memory. Now let's get into the code. So let's start by showing off the simplest form of a container that's an array. So to declare an array I just need two informations. The first one is the number of elements of this array, so in this case we declare n equals 6, and the second piece of information are the elements of this array. So I will declare an array of type float called x containing 6 elements. And I will declare here over the top just a method to help visualizing the elements of this array on the console. So let's call this method printArray, where we are going to pass the number of the elements of this array as n, and the elements inside this container as a float pointer named x. And here we just declare a for loop that will iterate over the n elements of this array, and print them on console separated by comma. Let's add a comma over here at the end, and at the end over here let's jump to the next line. That will help us to visualize more clearly different arrays using this print method. Now that our method is ready, let's call it over here. And let's pass the parameters n and x that we already declared over here, n for the number of elements and x for the elements itself. So let's just play here and see the results on the console. Well, we can clearly see here the 6 elements of the array printed on the console. Problem is that since we didn't initialize those numbers, we have just some garbage displayed over here. In fact, what we did was just reserve 6 spaces in memory. Well, probably those numbers are just end of scale, you know, for a floating point, but now let's imagine that we want to initialize our array containing 6 elements as 0. For that I need to come over here, and that just equals 0 between 2 keys. And if we run again, now we have 6 zeros here. Well, and now let's imagine that we want to declare a sequence of elements like 1, 2, 3, 4, 5, 6. Well, for that I just can go over here again and declare the 6 elements separated by comma, like 1, 2, 3, 4, 5, 6. Well, that's it, our 6 elements. Now let's see what happens if I decide to just declare 4 out of the 6 elements of our array. Just to be clear, despite the fact that I just initialized 4 elements, the remaining 2 elements were initialized with 0, meaning that this technique over here will initialize all elements despite the fact that we just assigned values to some elements. Now I would like to emphasize here on our variable x, our array, is that all its elements are stored sequentially inside the memory as we see in the console, meaning that they are organized in a vectorized format. Now let's imagine how we can link this concept with deep learning or artificial neural networks. So to start, let's imagine that we have a deep learning that accepts 3 distinct elements on its inputs. So let's declare a float A here with some random value, another float B with another random value, and the last float C with, I will put here a negative value. So the question is, how I can represent these 3 values in a vectorized format for our deep learning input? Well, I could simply declare here an array x1 containing 3 elements and store inside its elements the values of A, B, and C. And if we use our print function here, we will clearly see that all those 3 values will be printed sequentially inside the console. Well, we can check here on the console that all those 3 elements were printed in a vectorized format. In the end, we just put all those 3 separated elements A, B, C inside same container. This concept applies not just for arrays, as we saw in this example, as well as for other types of data structures like matrices and tensors, as we are going to see now. So let's switch now to data structures with more than one dimension. Moving on to 2-dimensional arrays or matrices now. For that, I will just clean up this code here. To declare a matrix, like we did in an array, I need to tell the number of elements for each dimension, meaning the number of rows and number of columns. On this example, I will use 2 rows and 3 columns. And now there are 2 options that we could use to declare a matrix in C++. The first one that I will show is the non-vectorized format, and the second one that we will keep is the vectorized format. For the first option, the non-vectorized format, I will declare the matrix on the stack like this. Let's start by declaring a variable that we will call A for matrix A, and then on the first pair of brackets we put the number of rows, in this case n1, and on the second pair of brackets we put n2 for the number of columns. And inside the main braces I can declare each row adding another braces containing its elements, like 1, 2, 3 for this first row and 4, 5, 6 for the second row. So this is the non-vectorized format where each row can be stored independently in different parts of memory inside our program. Now, if we want to work in a vectorized format, we could simply declare a matrix B that, instead of containing two pairs of brackets, contain just one, with the number of elements being the product between n1 and n2, and with its elements being declared inside a single pair of braces like this. I will just skip here the three last elements into the next line to help visualizing better the matrix. This format guarantees that the elements are stored sequentially inside the memory. Now let's create two methods to display those matrices on the console, the first one in non-vectorized format and the last one in vectorized format, just to see how we do that. I want to show you that even in the second example, that the elements are stored sequentially as an array inside the memory, we can display them as a matrix using index calculation. So let's start by creating a print matrix 1 in which I will pass the number of rows as n1, number of columns as n2, and the matrix elements itself. And since I declared the non-vectorized matrix on the stack, first I need to pass an empty bracket, meaning an undefined number of rows, but need a second bracket with the exact number of columns of our matrix implementation. If I had used the new keyword, I could use the double pointer notation. So here we start by creating a for loop that will iterate over each row defined as n1. Then we create a for loop that will iterate over each column defined as n2. And finally print each element of our matrix A by first putting the first bracket the index of y, and in the second bracket putting the index of our variable j, separated by comma. Let's jump a line for each row and jump a line for the entire matrix. And let's call the print matrix 1 to see the results. Passing the variables n1 for rows, n2 for columns, and a for the matrix elements. And let's run to see what the console will bring to us. But before, let's take a quick look of how our data from matrix A is stored inside the memory. If we open here, we can clearly see that each row is stored inside its own memory space. While if we take a look at matrix B, we can clearly see that all its elements are stored sequentially inside the memory, meaning in the vectorized format. Now returning to the console, we can clearly see that our variable A was displayed as a matrix notation like we wanted, with 3 elements in the first line and 3 elements on the second line. Now let's move to our matrix B and see how we can print its representation as a matrix notation. For that I will create another method called print matrix. I will not add a 2 over here because this is going to be our main print method that we are going to use in the future. And here I will pass the same parameters as in the print matrix 1 method, but with one minor difference. I will just pass a pointer instead of the matrix notation in the variable A, and that applies to any data structure in which its elements are stored in vectorized format. You just need in the end to pass a pointer for the first element of the sequence. The only difference in the end is the number of dimensions that we have to pass. So for example, if we have a tensor with 3 dimensions, we need to pass n1, n2 and n3 and so on. Now what changes in vectorized format when print the elements of our matrix is that we have just one pair of brackets, and inside it we have to get the index reference for each element. To do that inside a single bracket, we take the most inner dimension, that's index j, plus the next outer dimension, that it's index y, by the number of elements of its dimension, that in our case is the number of rows n1. Now let's jump a single line as before. And now let's see if we can obtain the same result as before using the matrix B in vectorized format. Yep, the same results. So we can see here that even with the elements of matrix B being stored sequentially inside the memory, we display them as a matrix using index notation. And the same principle can be applied to any arbitrary number of dimensions, as we will see in the future. Now that we saw the two distinct options that we have to declare a matrix, either using the row notation or the vectorized format, I will simply remove the first option because we are not going to work using that way anymore, since for now on all our data inside our deep learning is going to be stored sequentially inside the memory. Now let's show a little bit the advantage of working in a vectorized format that maybe you didn't think before. For that, let's return a little bit to our first example using an array. So let's declare again our array X containing 1, 2, 3, 4, 5, 6 elements, the same number of elements as our matrix B. And if we print that again over here, passing N and X, let's see what is displayed on the console, since both containers have the same number of elements. But if we check over here, they are displayed in a different way, because their representations are different. So in the end, we can say that an array can be a matrix, or a matrix can be an array, since the only thing that changes for one and another are the rules telling how many dimensions each container has, and how many elements are stored inside each dimension. So for example, if I declare a new container C with the number of elements as being the same number of elements as the array plus the matrix B, containing the elements of the array 1, 2, 3, 4, 5, 6 and the elements of the matrix 1, 2, 3, 4, 5, 6 as well, I am just jumping a line here for a better representation of the matrix elements, but they are all in the same sequence. Now if I call our method printArray and pass the number of elements of the array in our container C, and on the next line call our method printMatrix passing the number of rows, the number of columns, the container C, and an offset with the number of the elements of the array, let's see what happens. Let's jump a single line for clarity and run. Let's see how wonderful is that. See that I display the same result as in our array X in matrix B inside a single container C, just using the vectorized notation. So in the end, that means that I can have multiple data structures inside the same place and just play with the rules to display them, opening up for an infinite number of possibilities. Now I will show how we can make our lives easier by using a data type that has at the same time the number of elements as well the elements itself inside it. For that, here on the top I will add an include calling the standard library vector, and here instead of declaring using this notation the array, I can simply replace this by this notation. And this vector structure here is nothing but a dynamic array, so it can change the size during the runtime execution. We can see that all errors when we replaced the raw pointer by the vector structure were gone, but there are still some errors that Microsoft Visual Studio is trying to point to us. And if we verify what is happening, it's because we cannot simply pass the vector structure inside our print array method, but we need to pass the pointer for the first element of the array, and to do that we can simply call the data method. And if I try to run the program again, we should expect the same result as before. Now let's wait a little bit. The same results were displayed. Now the question is, how we can adapt the other data structures using this vector from a standard library. On our matrix B, I can simply replace this declaration by a vector of type float. I don't need anymore to specify the size inside this bracket. Call the data method here. Our C container the same thing. call our data method again. So the advantage of using a standard library vector container instead of a raw pointer lies on the fact that you don't need to worry about memory management, since it does for us. Meaning that we don't need to worry about calling the delete function after calling the new. Also don't need to worry about whose responsibility for taking care of this tedious process. Now running again our program, we can clearly see that we got the same result but with less overhead. So using the standard library vector container we get two benefits. The first one is the memory management, and the second is having the number of elements as well the elements itself in the same data structure, organized using the vectorized format. So in today's episode we saw how to work with different number of elements organized inside the same data structure called container with different ways on representing them using the vectorized format, meaning that all its elements are stored sequentially inside memory. The usefulness of knowing this lies on the fact that deep learning works with a large variety of data types, and in the end of the day, if we can simplify a spreadsheet, an image, a video, music and so on to a single format, the easiest our life will be. And that's why this introduction is very important. So that's it for today, thanks for watching and until next time.